For all of human history, we've gazed at the night sky and wondered what's out there. We built telescopes on land and in space and learned about the universe from what we saw. But what about everything we can't see? What if we could listen to things like the collisions of black holes or the explosions of stars? Einstein believed these events created ripples in the fabric of space. He called them gravitational waves. But he didn't think we'd ever find them.
The prediction of gravitational waves was made by Einstein 100 years ago. In that paper, he says, this is such a tiny effect that nobody will ever measure it. Well, I've always been an experimenter, and I did a lot of calculations on that. And I also guessed at what might be the strongest gravitational waves one would imagine. And I came to the conclusion after that yes, if you built this on a scale big enough, kilometer scale, you could do it. No fooling around. That was the beginning of LIGO everywhere.
I was a first-year graduate student at MIT, and when he first told me about LIGO, I thought he and the whole idea was insane. Gravitational waves are incredibly hard to detect. You can think of them as ripples stretching and shrinking space as they travel through the universe. They travel at the speed of light, and they pass undisturbed through every object that they meet. But by the time the gravitational wave gets to us here on the Earth, its effect is minuscule. 1,000 times smaller than the nucleus of an atom, and the nucleus of an atom is 10,000 times smaller than the atom itself, and the atom itself is 1,000 times smaller than what we can see with microscope. So just, to put a scale on exactly what that number means, I'll just say it in words. It's really damn tiny.
It took 100 years for the technology to get there. And now, why you ask this fundamental question, why bother with it? That's the way science works.
For over 40 years, more than 1,000 scientists have contributed to LIGO, where virtually every technology is pushed to the edge of what's possible. At the heart of LIGO is a laser interferometer that has to measure movement smaller than anything ever measured before. It begins with a laser that's split and sent down two 4-kilometer-long tubes to a mirror that reflects the laser beams back. These mirrors are so well protected from earthly disturbances that only a ripple through spacetime should affect them. If we measure a difference in the distance traveled by the laser beams, we know that a gravitational wave passed through the detectors.
Our detectors are essentially marking out, almost like survey stakes, points in spacetime. And if a gravitational wave passes, squeezing and expanding spacetime, then the arms look to us as if they change their relative length.
Once a wave passes through, we're able to encode this rumble of spacetime into a sound we can hear, if we're able to cancel out all the background noise.
So noise to us means anything that could disturb the readout of our detectors. It could be the tremor from a distant earthquake, or acoustic effects of thunder, glitches in the electronics, trucks on a nearby highway, even quantum noise in our lasers. We have to beat down the noise to have a chance of hearing a gravitational wave above that. And for 10 years, we searched for gravitational waves, but we didn't hear anything.
And then for the next 5 years, a new, more sensitive detector was put in. We got it running at the sensitivity where we felt we should just sit quietly and let it observe the universe.
I mean, what's the greatest pleasure I have in my life is to build apparatus, fix it when it doesn't work, and understand it, and it works.
On the morning of September 14th, 2015, we finally detected the best-looking signal we'd ever chased.
The signal that we measured is something called a chirp. It's the signal that you get from two black holes colliding.
They might have been doing this orbit for millions of years, perhaps a billion years, as they are in this sort of death spiral. This system is the most powerful astrophysical event observed, save for the Big Bang.
They're getting closer and closer and faster until they finally collide. Space-time becomes so warped, that's when most of the concentration of energy is released.
Those black holes that were doing that damn near smashed into each other at the velocity of light. That's got to be appreciated. So we were looking at extreme physics, and the equations still work.
So these gravitational waves traveled for 1.3 billion years before changing our arm lengths a few thousandths the size of a proton, making this the most precise experiment ever built by human beings.
Having worked with Ray for so many years and seen the passion that he brought to it, I just felt like this first one was for him. He more or less invented the field, invented the instruments, and this community of scientists, along with him, had pulled it off.
We have opened, thereby, a new field of looking at the universe. It's called gravitational wave astronomy. And it might tell us a lot of new things about the universe, which we don't know anything about. Okay?
Fighting fire with fire. Conventional wisdom says that's an exercise in futility. But at GE, we don't pay much attention to conventional wisdom. So we're going to conduct an experiment on Jason here to prove that you can fight fire with fire. Or, more accurately, with the sound of fire. The theory is intense bursts of sound cool flames, extinguishing them. Sound crazy? Well, actually, GE uses sound in a lot of innovations, including a new, more precise kind of mammogram that uses ultrasound instead of X-rays. But first, we need fire sounds. We'll need to mix these fire sounds to create the perfect frequency and intensity. We'll aim this sound at the fire with these modified speakers. Lots of them. Ready, Jason? Light him up. So, it seems you can fight fire with fire.
Sound.
And if we can fight fire with fire, imagine the other impossible things we can do.